Okay, let's welcome Jacob Tsimerman from University of Toronto. He's going to talk on maximal compact subvarieties of AG. Let's welcome.
Thank you very much. It's a great pleasure to be here. Um, I wanted to talk about some unexpected connections between functional transcendence and some classical questions in algebraic geometry. So we'll sort of start in the world of algebraic geometry and migrate our way over slowly. And the question is very simple. I should mention, as is written down here, everything I talk about is joined with Sam Gruszewski, Salvatore Mani, and Gabriele Mondello. So the question is the following. So suppose that X is a quasi-projective variety. The board's going to turn very slightly, so I'll keep adjusting it. We're eventually going to work basically over the complex numbers, but we can start over any field. And the question is, how far is X from being genuinely projective? So it's kind of a vague question, and we can ask it for any X. For most X, that's sort of hopelessly difficult to answer. And how do you measure this? Well, there's two sort of ways one can try. So these are like proposed answers to this question. One is you can measure it top down. So how much do you have to remove from a compactification of X in order to get X? So you can look at the minimal dimension over all compactifications, X and X bar, of the dimension of the boundary, minimal dimension of X bar set minus X. If you can compactify X with a point, this number is 0. If you need a curve, it's 1, and so on. On the other hand, you can measure X, or this quantity bottom up, and sort of build up from projective subvarieties X contains. So I'm going to define this slightly esoteric notation, mdim sub c of X. C is for compact, to be the maximal dimension of Y, where Y ranges over projective subvarieties of X. Okay, so the larger dimension a projective subvariety you contain, the bigger this quantity is. Now, this bottom-up measurement is lacking in some ways. Notably, you could have sort of one very large projective subvariety, but it sort of comes up for very special reasons. For example, take any X and blow up a point. All of a sudden, you've got a compact divisor. You might consider that to be not truly that close to being projective. So you have this variation of it, mdib sub c gen for general of X, defined to be the maximal dimension of Y, where again, Y ranges over projective subvarieties of X, which contain a very general point. So these Y's have to be everywhere. They can't be constrained to some Zariski closed subset of X. And this is sort of, for many purposes, a much more natural notion. Okay, so there are some obvious relationships between these, which I'll write down here. So first of all, MDC is at least as big, of X, I guess, is at least as big as MDMC gen, sort of for tautological reasons. And then only very slightly less tautologically, there's sort of a tension between the bottom-up and bottom-down approaches. Which is that if you have a compactification with a very low dimensional boundary, you can use Bertini's theorem, that's where this inequality comes from, to just build compact subvarieties which avoid that boundary that are larger and larger. So if you're missing a point, you have a compact divisor, which avoids that compactification, and so on. Okay, so we have the relationships between these, and again, in general, this is a hopelessly hard question to answer. So we're going to specialize quite quickly. And there's two cases of interest that we're going to consider. So the main one is AG. So the moduli space of principally polarized abelian varieties, just shorthand PPAV, of dimension G. There's a bunch of nuances here, none of which affect the answer. So there's some stack structure on AG. You can also ask why principally polarized, why not some other level structure. All this stuff is related by finite maps, and so it doesn't affect the sort of quantities that we're interested in. And so I'm going to fix this one for concreteness and pretend it's an algebraic variety. Sort of a very, very minor lie that doesn't affect anything. And just for context, the dimension of AG is G plus 1 over 2. Okay, so let me start by summarizing what's sort of known about this case, and we'll talk a little bit about arbitrary fields before specializing back down to C. So first of all, if you work over FP bar for some finite field FP, that's going to keep happening, I apologize, then you get a lower bound of G minus 1 over 2, stemming from those abelian, the locus of those, this is AG, stemming from the subvariety parameterizing those abelian varieties whose P torsion is connected. This gives you some very high dimensional projective subvariety. There's no analog of this over the complex numbers, so you might ask, can you get something this high over C? And it was proven by a famous result of Kio and Sadoun, sort of very early result using some what's going to come to be known as functional transcendence theory, that over C, what they proved is you can't get this high. They literally proved this inequality. That's right. So this is just about MDMC, not MDMC gen. That's right. No. It's a great question. And then finally, there's the work of Bailey-Borel, who did not specifically ask about this question, but they produced a compactification of AG with a pretty high codimension boundary divisor. And so just applying this inequality over here, what they end up showing is that MDMC gen, actually, over the complex numbers, is at least G minus 1. If you take the Bailey-Borel compactification, you keep intersecting with random hyperplane sections, you will build a G minus 1 dimensional compact subvariety, avoiding the boundary. Okay, so the theorem I want to talk about, due to these four authors, so GMST, is the following. So first of all, if we just talk about MDMC gen over the complex numbers of AG, so the maximal compact dimensional or projective subvariety of AG through a very general point, it's exactly G minus 1. So the Bailey-Borel argument is tight, which kind of as a cute consequence of this, it gives another proof of the fact that there's no compactification of AG with an even higher codimensional boundary, which you can prove in other ways, but sort of a cute consequence of this. And then if you look at this quantity, where you just want compact dimensional subvarieties, you don't care if they're through a very general point or not, the answer becomes at least more interesting to write down. So up to 15, give myself space. So if G is less than 16, the answer is G minus 1. And as soon as G is at least 16, you get the following quantity. It's a little silly to write down, but I will nonetheless. So it's pretty much G squared over 16, but the exact value is G over 2, sort of rounded down, squared, then over 4, rounded down again, as soon as G is at least 16. So you get this sort of precise, a little funky looking answer. So just a couple of remarks about the structure of these compact subvarieties. So first of all, what is very general can sometimes be very hard to specify. You have to take the complement of countably many algebraic subvarieties. In this case, it's quite concrete. So the notion of very general that suffices for this result is just containing a Hodge generic point. As soon as you have one Hodge generic abelian variety, and you're compact, your dimension is at most G minus 1. And the second remark I wanted to make is that if you look at these high dimensional compact subvarieties, you might ask sort of, is there just one or two? And the answer is no. They're in fact topologically dense. The set of all of them, if you union them, they're topologically dense in AG. And this is in fact not a deep observation. You can, regardless of what MDIM gen is, you could have predicted this ahead of time. And the reason is just that you have, as we'll talk about more later, you have Hecke operators in AG that if you hit one compact guy where you get other compact guys, Hecke orbits are dense, and so you get all these different guys floating around. In fact, if you quotient out by sort of the equivalence of isogenies, these Hecke operators, you still get it to be topologically dense. So this is not the only reason, but it's sort of a cute reason you can see right away. And because a picture can be worth a 1,000 words, if you'll indulge me for just 1 minute, I'll draw this little table here with these numbers just to get a sense for what they are. So values of G, and here's the dimension of AG, the Kiel-Sadun bound, and the two actual answers for what MDIM-CGN and MDIM-C are. So I'll explain how things start out with 3 and 4, and then we'll jump to 16 and 17, where a little phase transition happens, and then we'll jump to 100. For big numbers, you can see what's actually going on. And here are the numbers. Okay. So MDIM-CGN is not so interesting. It's just G minus 1. Goes on forever. And that actually becomes best up until you hit 16, where you get a little bit of a shift here. The same at 17, and then it starts growing quadratically, roughly like this number divided by 8. And so the Kiel-Sadun bound sort of saved the linear factor, and here we have the answer, which is quite a bit lower. Okay, I don't know if tables are helpful, but hopefully they give some kind of sense. Okay, so before going into the proof of this result and its relation to functional transcendence, let me say something about the consequences for another moduli space, MG, an MG compact type, or you could also ask this question. It's in fact even more interesting for these two moduli spaces, looking for basically compact families of either curves, and these are sort of curves of compact types. You have at most nodes going on in the tree structure. So why does this AG result give you anything about MG? Well, it's because you have Torelli maps. MG compact type has a map to AG, got to call J for Jacobian. This is in general a proper map. It has a lot of fibers, because if you sort of take two curves, you can join them at any node, and they'll give you the same Jacobian regardless of which point you're joining them at. If you look at smooth curves inside there, then this actually embeds up to some stacky issues we're not going to worry about. Not just to AG, but in fact to the indecomposable locus of AG. So it's AG minus the union k equals 1 to g minus 1 of ak cross ag minus k. So these are abelian varieties which are indecomposable as principally polarized abelian varieties, together with the polarization as well. That's important here. This, of course, lives inside here. So then you can take these results and you can try to apply them to these two spaces, because if you take a projective variety here and you push forward, you'll get something here. So what was known before? So before we had this result, well, not we, but there was this result, that if you look at compact subvarieties of Mg, the best known upper bound still to, I think, my knowledge, this is by Diaz, is G minus 2. And the best known lower bound, this is by Zal, is log base 2 of G minus 1. I guess rounded down. This is for G at least 3. So there's quite a large sort of gap here between lower and upper bound. Essentially, this lower bound construction, you sort of make these projective families of curves by taking iterated ramified coverings of curves. You sort of add a dimension every time you double the genus, more or less, is the way that this works, whereas this bound is much closer to the methods we're going to be talking about. And then, so the Keelan-Sadul bound already implies something a little bit new. If you apply it to Mg compact type, Keelan-Sadul implies that MDMC Mg compact type is at most 2G minus 4. And then we have, in some small ranges, we have some new results. And essentially, it's easier to apply results to Mg compact type because the fibers of this map are actually really big, which helps the analysis. This is for G between 2 and 23. We get this exact equality. If you look at instead the image of this, the abelian variety, just the Jacobians, we get a bound of G minus 1. And there's one more I want to mention, just because it's so tantalizing. If instead of AG, we look at MDMC gen of AG indecomposable, it's certainly bounded by that of AG, which is G minus 1. You can give a lower bound of G minus 2 pretty easily, because you're moving a divisor of dimension 1 more than the boundary. And then it becomes very tantalizing, because you're off by 1 to ask which one is actually true. We tried figuring it out. We could not. For G equals 2, 3, and 4, this one is correct. 2 and 3 were sort of classical. 4, we have some argument with intersection theory. So I don't know. Based on this evidence, maybe this is always right, but who knows? And it's just kind of an interesting aside. Okay, so those are the consequences for Mg. Maybe this is a good point to stop for questions in case people have some questions before going into the proof. Yes? Oh, when was this? Ooh, I'm sorry. This is really not my field. I don't remember. It's in the paper, yeah, but I don't remember it offhand. Apologies. Other questions that maybe I can actually answer? No. Okay, that's all good. All right. So let's move on to the idea of the proof. And to start, we'll set things up in the following way. Since we have so many compact subvarieties of dimension G minus 1, those are not sort of interesting. So suppose we have an X in AG, which is projective, and the dimension is at least G, will be our starting assumption. And the idea is the following. There exists in AG this almost embedding. It's a finite map. I'm going to call iota of A1 cross AG minus 1 to AG, which is just you take an elliptic curve and a abelian variety of dimension G minus 1, and you direct sum them. And the codimension here of the image is G minus 1. Which means that if I fix a point here, I fix the elliptic curve, I get something of codimension G, and naively, you would expect the image to intersect such an X. Of course, that's very naive. It's not always going to be true, but that's sort of a reasonable a priori expectation. So the first key observation is that as, I'm going to write a little bit loosely, as your elliptic curve goes to infinity, sort of degenerates to the cusp, in whatever sense you want to think about it, this whole image also degenerates to the cusp. So topologically speaking, the limit closure of the set becomes sort of the empty set. Which means that for large enough E, it can't intersect our X, because our X is compact. It stays away from the boundary by assumption. But everything here is algebraic. So we conclude that for almost all E, this is my for almost all notation. I promise it won't get confusing. The intersection of X with this set is empty. Because it's eventually empty, and this is a curve, so everything's constructible. And more importantly, what we conclude is that for all elliptic curves, if I look at this intersection, well, if it's not empty, then all the nearby ones do have to be empty. Now, by assumption, we expect it not to be empty. The expected dimension is not 0, which means if the expected dimension is ever correct, the nearby guys would also not be empty. So as a corollary, this expected dimension is never correct. So it may not be empty, but this is nowhere of expected dimension, which I'm going to instead say nowhere likely, in keeping with the jargon of unlikely intersections and functional transcendence. Okay, so that's sort of a cool thing to notice, but by itself it's of course not useful, because your X might just not intersect this whole image, and then you've learned nothing about anything. So we want to take this property, which I'm going to call star, and we want to upgrade it to something we can actually study. In particular, it's much more useful for us if we produce a non-empty intersection somewhere, which has this property. Okay, so the first upgrade is the following. To start, let's remind ourselves, as we slowly transition to functional transcendence, that we have this Siegel upper half space consisting of symmetric G by G matrices, whose imaginary part is positive definite. So if G is 1, it's the upper half plane. If G is not 1, it's some higher dimensional version of that. We have an action, a transitive action, with compact stabilizer of the symplectic group on HG of biholomorphic automorphisms, such that if you look at HG mod, oh boy, let me go over here. If you look at Siegel space mod the integral points, you get a transcendental uniformization of abelian varieties, just basically by uniformizing the abelian variety and considering the symplectic lattice. That's what happens over here. Now, if we take an element of rational symplectic matrices, then we can look at the graph of sort of acting by H. This gives you a biholomorphic automorphism of Siegel space, but it will actually descend to something algebraic here, given by taking isogenies of a certain type. So this gives us an algebraic correspondence, some sort of the Heck operator corresponding to H inside AG cross AG. And what we can do for all of these Heck operators is we can take this whole picture and we can apply the Heck operator to every single one of these guys. And I'll get some other family of AG minus 1 translates, so something with level, which degenerates to infinity, parameterized by a curve. I can apply the exact same analysis. And what I conclude here is that for all H in SP2GQ and elliptic curves E, if I look at X intersect the Hth Hecke operator to this set, because AG minus 1, this is nowhere likely. Which is like an upgraded version of star, which I'll write as star sub q. Okay, so now we have some dense collection of subvarieties, all of which are supposed to intersect X by naive dimension theory. And we know that either they don't intersect X, or if they do intersect X, the dimension is too large, larger than expected. This is already sort of a little bit more, but it's still not sufficient because one still can't show, on account of it not being true, that there exists some H like this, such that X actually has to intersect this set. Sure, it's some countable dense collection of subvarieties, but X could, and sometimes does, avoid them all. So now, finally, we're going to upgrade to actions by real elements H. Now, of course, we have to leave the realm of algebra temporarily and enter the realm of transcendence. And the thing to observe is that these Hecke correspondences, even if you think about the modular curve, as algebraic varieties, they're extremely complicated, right? Their degree grows, there's something interesting, but locally they're all very simple. There's some sort of foliation or multifoliation, more precisely, that's going on inside the product, and these are just happen to be algebraic sort of sections of this multifoliation. So we can instead ask about non-globally algebraic sections of this multifoliation. Speaking about this more concretely, let's look at this uniformized version of iota tilde, mapping from the usual upper half plane across the G minus first Siegel space to the Gth Siegel space, which in terms of matrices is very simple. Let's just look at block diagonal matrices, better than side here. Sort of a lift of our iota. We can look at X tilde, which is just the inverse image of X, which lives inside AG, inside of our Siegel space. And now for all H in the reals, the real elements of the symplectic group, we can consider X tilde intersect H dot iota tilde of Z, some element in the upper half plane, cross HG minus 1. So this is just a lifted version of this algebraic guy if H is rational, and if H is not rational, it's something which does not lift anything algebraic. Project it down, you'll get some dense sort of leaf. Okay, but analytically, as H varies, this is a perfectly reasonable family of varieties. I can even consider complex H locally. And this behavior is generic in H, and the rational points are dense. And so if I ever had this intersection be the correct dimension for some real H, I would also have it for some nearby rational H, which would contradict this. So what I'm learning is that this intersection is nowhere likely. Okay? And this finally is useful because the real points of the symplectic group act transitively on Siegel space, so I can just force this intersection not to be empty. I can do it in many different ways, in fact. So I can take any one of these leaves of my multifoliation and learn that something unusual happens. Okay, so here's where transcendence theory comes into the picture. Check how much time I have, depending on which I will give different forms of this introduction. Okay, some time. So, So how to think about this sort of intersection? There's sort of many different perspectives one can take. One can take a differential theoretic perspective. One can take a transcendental perspective, an O minimal perspective of model theory. But the basic idea we're going to take is we have this transcendental map pi from Siegel space to AG. Here we have some algebraic structure given by the fact that AG is an actual algebraic variety. Siegel space is not an algebraic variety, but it's inside of an algebraic variety. It's an open domain inside of an algebraic variety. So it still has a semi-algebraic structure. I can still meaningfully talk about germs of algebraic things in here, inside here. And the idea is that this transcendental map should basically be blind between these two different algebraic structures. It shouldn't mix them at all, except for when it sort of has to mix them. And yes? Oh boy. Yes, sorry. So I'm equivocating. You're right. My pi is now, I'm looking at a map from HG to AG. This map pi is an isomorphism once I close it out. You're right. I'm being a little sloppy. Thank you. But the idea is that these two algebraic structures should have nothing to do with each other unless there's some reason for them to have to do something with each other. And the only reason is sort of the theory of Shimura varieties, or Hodge theory, depending on your preferred language. Here, what do we have? X is something algebraic in the bottom structure, which I'm viewing in the top structure by pulling it back. This here, if I project it down to AG, I get nonsense, but viewed inside the space of symmetric G by G matrices is just some linear subspace, so it's something algebraic there. And the fact that the intersection is nowhere likely, the dimension is larger than expected, should be viewed as some sort of relation between these two algebraic structures. So functional transcendence theory tells you that something special has to happen. So let me present a theorem which is known as weak X Shanuel. So in this form, it was proven by Naming Mock, Jonathan Pila, and myself, but then based on works of Ulmo and Yafev. And an important feature in this theory is the work of Andrei and Delin, or a work of Andrei based on work of Delin. So the name is weak X Shanuel because it's based off of a work of X, which sort of proved analog of Shanuel's conjecture in the case of function fields. The nomenclature requires its own little lecture to understand. But by now this is standard, I promise. And what it says is the following. Suppose you have an algebraic variety V in AG and a semi-algebraic variety W in HG, which you can just think of as an algebraic variety inside here, intersected with this guy. And look at a component of their intersection, meaning you take V and you pull it back under pi, and then you intersect with W. And suppose that this has larger than expected dimension. It can't be smaller, it can only be larger. Well, then it must be accounted somehow by Hodge theory. So one way of stating the conclusion is that there exists some proper subvariety S in AG, which is what's known as weakly special. So it's essentially a Hodge locus. It's really a translate of a Hodge locus. That's your language, but it basically comes from a Shimura variety sort of translated in some way, such that the projection of this intersection lies inside S. So basically all unlikely intersections are accounted for by these weakly special subvarieties, which are somehow Shimura subvarieties. Okay, so now to prove the first part of the theorem, MDMC gen, this already suffices, because if X is Hodge generic, then X contains a Hodge generic point, and you can show that those don't lie on any proper weakly special subvarieties. So you automatically get a contradiction. This is a contradiction. Yes. S is an algebraic variety. You should think of S, I didn't see who asked the question, but you should think of S as something like a fixed elliptic curve cross AG minus 1. That's the kind of thing that S is. Okay, so if X is hard generic, this is already a contradiction, and the proof is complete. So in the general case, we have to work a little bit harder. So the first thing we have to do is we have to run this argument not just for AG, but for special subvarieties of AG, because you might be a non-general X might have a very constrained non-Forte group. And so we need this, I'm going to write this here. This is a very cute little lemma, which it's impossible that it's due to this paper, but I could not find it anywhere else, so I just want to say it out loud, which is that every non-compact, non-projective Shimura variety contains a modular curve as a Shimura subvariety. Okay, so once you know this, you can basically play this game inside arbitrary non-compact Shimura varieties. And there's a corollary. What we learn once we play this game is we actually get a pretty concrete classification of all maximal compact subvarieties of AG. So if X in AG is not just maximal dimensional, but a maximal compact subvariety, then there exists a K such that you can break up X in the following way. You have a map, which I'm going to lie and pretend this is an injection. It's a finite map, but who cares? You break up AG into AK cross AG minus K. Inside here, you have an S. Inside here, you have an X prime. And X breaks up as a product like this. And what are these S and X primes? Sorry, is this visible in the back? It must not be. Okay, let me rewrite it. I apologize. So you have a AK cross AG minus K sitting inside AG. Inside here you have S. Inside here you have X prime. And their product is X, where S is a compact Shimura variety. And X prime has the expected dimension. It might not be hard generic, but its dimension is G minus K minus 1. It's the same thing you would get with the hyperplane argument. So as a consequence of this, all you need to do in order to solve the question, to understand the maximal dimensional compact subvarieties of AG, is to understand the maximal dimensional compact Shimura varieties of AG. Okay, so you do this now, so you know. Need to understand these. And this is some, for us, this was by far the most work, but it's not the most interesting part of the result. It's heavily used as sort of work of Satake and Milne. It's sort of an analogous question to understand. Understanding Shimura subvarieties is sort of similar in spirit to understanding semi-simple subgroups of like sp2g or something like that. Say no. It's annoying, but ultimately you can do it in most of its quadratic forms. Okay. So let me now give an example of this maximal dimensional guy. That's kind of cool, because you can write them down reasonably explicitly. So what you do is the following. This is essentially the only example. I mean, there's minor variations of it, but we can and do show this is basically it. You take F to be a real quadratic field. you take E over F to be a totally imaginary quadratic extension. So F is a quartic CM field over Q. Now you take H on e to the g to be a Hermitian form. Hermitian relative to the complex conjugation of E over F. Of signature, now you get one signature for each of the two real embeddings of F into the real numbers. And so the signatures we're going to take are 0G at one place. So this ensures our Shimura variety will be compact. And then as tight as possible at the other, this maximizes dimension. G over 2 rounded up, G over 2 rounded down at the other place. This gives us an embedding of groups. UH, the unitary group, sits inside the general symplectic group of dimension 4G, so the dimension of e to the g. And this gives us a corresponding embedding of Shimura varieties, S of H into A2G. And you can check the dimension here is just the product, G over 2 rounded down times G over 2 rounded up. Okay, so then this yields all the highest dimensional examples, and you can show there's essentially no other ones. I mean, there's something to be said about level structure, something to be said about twists, but in terms of like the real Hermitian symmetric spaces, this is the only thing which can happen. Okay, so that's the story over C, and now I want to briefly get back to finite fields, or characteristic P fields. So, conjecture. This is my conjecture in that I'm not sure my co-authors are as confident as I am this is true, but all based on this work. So if it's wrong, it's only me to blame. If you look at M dim C generic over FP bar of AG, I believe it's still G minus 1. And the interesting thing about this is you can attempt to run the same sort of argument that you did before. Now, obviously, you don't have a complex uniformization. Nonetheless, you still have sort of local Serre-Tate coordinates. So what sort of, I'm going to write like a squiggly line for, not quite implies, but is strongly relevant to this conjecture, is the following conjecture in what I'm going to call formal functional transcendence theory. Which is the following. You can take a point X in AG FP bar, and let's take it over the ordinary locus. We're asking about generic guys anyway, so we may as well stick to the ordinary locus. It's not going to change stuff. So then here, what you can form is the formal Serre-Tate torus, which is a torus of dimension AG, which is the, it be identified with the completion of AG at X. And now inside here, you have sort of two different classes of things. On the one hand, you have things which are formal algebraic in torus coordinates. So sort of pick multiplicative coordinates and write down equations with those. On the other hand, you have germs of algebraic subvarieties of AG, which is sort of analogous to what you had in the complex case where you have the structure from Siegel space and the structure from AG. And now the question is there some sort of X-shanual result in this context, where I'm not sure exactly what it would be, but a natural guess is if you have an intersection of dimension larger than expected, is it, for example, the reduction of some Shimura subvariety? Is already not a crazy question to ask. And if you could answer that, then I think you'd be pretty close to proving this here. All right, thank you very much for your attention.
Yeah, thank you for the great talk. Is there any question from the audience?
So in the first part of the proof where you use the weak x channel, I just have a silly question.
Yeah.
The contradiction was the pi of u would be inside of some special s.
Yes.
But the x is Hodge generic.
Yeah.
But why is it the pi of u is just some subvariety inside of x? Why does it have to have Hodge generic things in it? It's just some subvariety.
Oh, yes, great question. So you can force the U to contain any given point of X. Because in the end, we were intersecting with translates by an arbitrary real element protected group, but it acts transitively. And so you just pick some generic point, and then there's no weakly special is contained in two. So there's no chance to get started.
Other question? Okay, let's thank speaker again.